So this lesson is all about modeling exponential decay. And when you're modeling exponential decay, you're going to have something like this. F of x equals a times b to the x. Now a is the initial amount, and the b is the growth factor. And for exponential decay, the growth factor has to be greater than 0 and less than 1. And that's assuming positive x. So b can also be 1 minus r, where r is the decay rate. So let's say you have a bag of M&Ms and you decided you want to eat 30% of the bag each day, and you want to model that. So 30% is actually going to be your R value. That's your rate of decay, or 0.3. That means your decay factor, B, is going to be 0.7. That means 70% of the M&Ms are going to be remaining. This model is for the M&Ms that are left in the bag, not for the M&Ms you eat. And how many M&Ms are in a bag? Like 40? Okay, so 40 M&Ms times 0.7 to the x, where x is the number of days. And this will work if x equals 0 is day 0. So what that means is you're assuming you're not eating any M&Ms on day 0, and you start eating M&Ms on day 1. So in other words, initially there'll be 40 M&Ms in the bag, then on day 1 there should be 40 times 0.7 to the 1 power, and that is 28. So there should be 28 M&Ms left after day 1. And you need to know what day you're starting this, just so you can follow the model correctly. And another way to look at this would be with a negative exponent. So you could say f of x equals 40, and then 1 over 0.7 to the negative x power. That could also be exponential decay. So an estimate of this, I'm going to say it's 1.43 roughly to the negative x power. Both functions represent the same thing, but this one's just rounded a little bit. So you can use positive or negative exponents, you just have to be careful about that. And if you have a negative exponent, your growth factor or your decay factor, as the case may be, should be greater than 1. If you have a positive exponent, it should be between 0 and 1. So that's the big picture for this lesson.